Kim.
Thank you for a nice presentation, Professor Balla. My name is Heung-Kyu and today my presentation topic is crystal plastic FEM simulation of grain by grain deformation. Most of presentation material is based on my PhD work, and some part of material is based on recent my study work. And as he introduced me, I am a mechanical engineer, not material scientist, and so my research interest or research viewpoint may be somewhat different from a material scientist like you. But anyway, my topic is related to gift, and I try to present this material to you. My research motivation is related to the microforming technology. I don't know whether do you know the microforming technology. There are many applications of microforming technology. The first picture shows the micro punching. This is the very small size micro hole on the metal sheet, very thin sheet. And this application is used for inkjet printer head. This hole is used for nozzle for nozzle of inkjet printer head. This shows the micro punching process. And this picture shows the micro sheet metal forming. This sheet is very thin, actually copper foil of thickness of 3.0 micrometer. Although this product has little applications up to now, but if you think the bipolar plate of fuel cell, it may be used for that product. As the thickness decreases, the whole cell size or weight can be reduced. And extrusion or forging can make very small micro machine element. This element can be used for constructing micro machine or micro robot. And this shows the micro embossing process. In this process, the sharp edge or sharp corner should be defined well by this technique. And in this case, the material should be fine-grained for superplastic deformation. In the application of microforming technology, there are various well-known phenomena called side effect. The first side effect is the flow stress side effect. Do you see the two cylindrical specimen? If you compress two specimens, you can obtain the load displacement curve, and based on the data, you can obtain the flow stress curve. Then the flow stress curve does not converge to one curve. In the macro scale, large scale deformation, we cannot see this phenomenon. But if the specimen is very small, that is, if the specimen, the size of the specimen is comparable to the grain size comprising the specimen, the normalized flow stress is different depending on the specimen size. I think you know where the microindentation test. In this case also, you can see the size effect in the flow stress, exactly the hardness value. If you change the indenter size, the observed hardness of metal is also changed. Generally, as the indenter size decreases, the hardness increases. It is also from the relative size of grain and the indenter. It is another example. Now, if you conduct torsional test on this rod sample, then you can obtain different flow stress curve from this experiment. This also due to the fact that there are the specimen size different, but the grain size within the specimen is almost the same. So the relative size ratio of specimen and grain is different. And then you can see the size-dependent flow stress curve. In addition to the flow stress side effect, there are side effects in friction. This is the double cup extrusion test. In the macroscale forming, if you perform this test, the cup depth or cup height would be almost the same in the upper cup and the lower cup. That is, the ratio of HU over HL is almost unity. But if the specimen size decreases as much as the match, but then the ratio deviates from 1. It is because the deformation behavior around the punch is not the same in the upper cup and the lower cup. The relative grain size is very large, so the grain randomness, the random orientation of grain influence the frictional behavior. Do you know where the microstructure evolution? In addition to the size effect or overall load behavior, there are various deformation behavior or subgrain deformation behavior. And one of the well-known subgrain deformation is grain refinement, grain splitting. ECAP is a good application of subgrain deformation. And in this case, also we can see you can refer to this phenomenon as the microforming, actually microstructural forming behavior. This was the introduction to my presentation. And first, I'd like to show the experimental observation of grain by grain deformation. As we are not a specialist in material scientists, our method may be primitive in terms of specimen preparation or heat treatment. Anyway, we prepared specimen of aluminum, pure aluminum, and in order to magnify the grain size, enlarge the grain size, we conduct heat treatment twice. One is heat treatment at 50 degrees Celsius, and then we conduct heat treatment at 450 degrees Celsius. And then we machined the block, cube-shaped block from the raw material. Then you can see that the initial grain size is increased much than before. I think that it is a misspelling. It is the grain size is smaller than this value. Anyway, after two-stage treatment, we can enlarge the grain size of specimen. The purpose of heat treatment is to make large the grain size, and then we can observe the grain deformation more easily. We measure the grain orientation by EBSD. We have a lot of specimens, and then we can select two types of specimen among them. One is a nearly single crystal specimen. Although there are small crystals, but roughly speaking, it is a single crystal. But it is a polycrystal. As the grain size increases by heat treatment, the number of grains is not so much. It's not too much, but too many. But anyway, we can refer to these samples as polycrystal specimen. And then we conduct compression test for the prepared aluminum block specimen. This is the surface picture at six surface. And then, if we compress this specimen, the deformed shape is as follows. As you see, the cube specimen deformed very strangely. The surface, the initially flat surface, distorted very much, and flat surface becomes curved and irregularly deformed. In case of a nearly single crystal, you can see that the initial cube shape deforms, but the flat surface remains flat after deformation. But in case of polycrystal, the flat surface changes into a very curved surface. It is very strange, but you can see that it is due to the grain comprising the original specimen. This shows the six direction view, and very distorted deformation. In order to measure the surface and store the data, we measure the surface profile by using non-contact 3D measurement. Then, following this procedure, we can make a CAD data based on the surface profile of deformed specimen. As you see, the actual specimen, the shape of actual specimen and the shape of 3D CAD model is almost the same. It is a natural consequence. Then, although it's a mechanical engineering method to represent the 3D structure, and based on the CAD data, we can examine the surface morphology or surface profiles. Now part 2. Now I'd like to show you the crystal plastic FEM formulation and simulation of grain by grain deformation. We want to know how to predict the size effects observed in the microforming processes. And second, we'd like to know how to predict the forming process concerning the grain by grain deformation before. And eventually, our purpose is to develop FEM formulation capable of predicting forming process in grain scale or sub-grain scale. Let's see the grain by grain deformation, experimental grain by grain deformation once again. The first, we have to know the concept of strain gradient effect. Strain gradient effect is observed in these cases. First, strain localization, strain gradient effect is observed. The example is indentation and crack tip deformation. Also, in case of material heterogeneity, the strain gradient effect is observed. The first example is when hard particles is included in the base material. And this is the granular material, polycrystal material. In fact, all these cases is based on is related to the localized strain deformation field. That is, there are high level of strain gradient around deformation zone. So, usual strain hardening effect, there are strain gradient effect in hardening, material hardening. In the theory of strain gradient, the strain gradient can be decomposed into stretch gradient, and rotational gradient. And mechanically, there should be a work conjugate for each strain measure. For strain gradient, the work conjugate is high order stress, and for stretch gradient, the work conjugate is double stress. And for rotational gradient, couple stress is a work conjugate. Strain gradient theory is, although the strain gradient theory is a complete theory, couple stress theory, which considers only couple stress and rotational gradient, is a good simplified model. And we think that in order to simulate grain deformation, crystal plastic model is a good formulation model. And the size effect or strain gradient effect can be modeled by strain gradient theory, strain gradient energy theory. In terms of dislocation model, we can, it is known that strain work hardening is related to the statically stored dislocation, SSD. And strain gradient work hardening is related to the geometrically necessary dislocation, GND. This slide shows the formulation for virtual work rate principle. In order to formulate FEM model, we have to make a virtual work rate principle. Finally, we make this type of formulation. Of course, this formulation is not a unique one for us. It is a well-known formulation for strain gradient formulation. Let's see the virtual principle again. In user FEM formulation, there are strain work term and external work term. But in case of couple stress or strain gradient formulation, there should be high order stress term and high order boundary traction term. Of course, there are another method of strain gradient formulation, which does not include this term. But in strong formulation, in strong couple stress formulation, this additional term is included in the virtual work rate principle. For the stress work term, we can use the well-known constitutive model of stress based on crystal plasticity model. We use the rate-sensitive self-system model. And in case of for this high order stress term, we assume a constitutive model. And this shows a brief summary. And in this constitutive model, we assume that the couple stress, high order stress or couple stress exactly, is a function of curvature, material curvature. And then we have to this form was assumed by us. And for this term, we have to assume the value of CV. The CV is the couple stress hardening coefficient. It determines how much the couple stress is hardened by the function of curvature. And through simple calculation and assumptions, we can guess the value. And now we can perform FEM simulation based on couple stress crystal plasticity. We consider the simple compression, actually plane strain simple compression test. And first, we examine how the couple stress influence on the load curve. This figure shows the result. As the couple stress hardening coefficient increases, the flow stress increases accordingly. This is a natural result because as additional hardening was included, additional hardening in terms of couple stress was included in the virtual work rate principle, the overall hardening will be increased if the coefficient increases. That is, load increases monotonically with the value of CV. In addition to the load curve, we can observe the deformation behavior. like this. As the couple stress hardening coefficient increases, the deformation patterns, the mesh shape becomes stiff, straight, stiff. That is, the surface profile becomes stiffer, straighter, as the couple stress hardening coefficient increases. This model is a single crystal model. From this observation, we can see that couple stress is related to subgrain deformation. If you examine the misorientation across the element boundary, then we can plot the misorientation value as a function of time step. Like the surface profile or deformation pattern, the misorientation, overall misorientation decreases as the couple stress hardening increases. This means that as the couple stress hardening increases, the deformation is more suppressed. As the deformation is more suppressed, the misorientation decreases and the surface profile becomes straighter. That is a higher level of constraint. Now we consider bicrystal model. Bicrystal model is composed of two grains connected in serial in the compression direction. And we assume crystal orientation for each grain, and then we simulate the compression behavior. This shows the deformed mesh shape after about 30% reduction in height. You can see that there are very distorted deformation. This is the user effective stress in formices stress. And this shows the couple stress contour. The couple stress, effective couple stress was defined like the effective stress. That is, in terms of formices type, formices form. You can see that higher value is observed around here and there, and this is the grain boundary region. And this shows the grain orientation contour in two-dimensional concept. You can see as the original bicrystal is composed of two grains of different crystal orientation. The upper crystal and lower crystal has completely different orientation. But in the upper crystal, the orientation is different from between this region and this region. And maybe this diagonal line is the boundary of two subgrain deformation region. We apply another combination of orientation, and as the bicrystal has different crystal orientation, different deformation was observed. If you examine the couple stress along this line, you can see that the couple stress increases as approaching the grain boundary. This means that higher couple stress value is observed around the grain boundary. As couple stress or strain gradient effect is related to GND geometric SL dislocation. It is a natural prediction. We applied symmetrical rotation combination to bi-crystal model. And as the crystal rotation is symmetrical, the deformation is also symmetrical across this grain boundary line. Now, again, let's see the deformation pattern and experiment observation. In fact, the grain orientation used for FEM simulation is different from the experimental specimen. The experimental specimen has a three-dimensional irregular orientation, and this is a more simplified two-dimensional orientation. So quantitative comparison is difficult, but we can compare two results qualitatively, and we assume that this FEM simulation can simulate experimental observation whether good. From the comparison with the experimental observation, we could know that the surface profile of grain, from FEM simulation can be controlled by the coupled stress hardening coefficient. By increasing the hardening coefficient, more stiff, more straight surface profile can be obtained. Or vice versa, if we apply small value of coupled stress hardening, the surface profile would be very curved than straight. And so we assume that incorporation of strain gradient or coupled stress may be a good method to predict grain by grain deformation. Up to now, we consider the grain by grain deformation in terms of surface profile. Now, we consider the subgrain, intragranular deformation behavior rather than the surface profile. We want to know how to predict subgrain deformation. As I explained in the introduction, grain refinement process is a result of subgrain deformation, large amount of subgrain deformation. This is the Mohammed equation. It is used for prediction of grain size after grain refinement process. This empirical correlation provides the grain size after large amount of plastic deformation. But we can know only the final grain size instead of the process of grain refinement. And we can study the subgrain deformation or subgrain phenomenon by examining the GND density behavior. That is, if there are high level of GND, there may be a new grain boundary. That is, new grain boundary was newly generated, around high level of GND density region. This result is from the Otis and Repetto, and this shows the dislocation structure determination. This research is about the dislocation structure determination based on energy minimization. Energy minimization is a basic principle in mechanics, and they try to determine the dislocation structure based on energy minimization. And subgrain deformation or grain by deformation is based on the dislocation behavior, dislocation mechanics. We can assume that the subgrain deformation behavior is also closely related to the energy minimization. This picture is from the paper of Basson and Driver, and they showed they observed the slip traces on the compression phase after the onset of deformation bending. They studied 3 different materials: aluminum, copper, and nickel, and they have different stacking fault energies. Aluminum, the stacking fault energy of aluminum is 166, and copper and nickel has these values. And aluminum has high stacking fault energy, and nickel and copper is smaller stacking fault energy among these. And they see, according to their research, we can see that the slip trace, you can see the slip traces in the picture. And this is a deformation bending. Of course, at this time, there are no grain subdivision or grain splitting at this time. But if the deformation proceeds further, then there may take place subgrain deformation, including grain subdivision. The red line, I draw red line on this optical measurement. The DSG, the magnitude of DSG means the magnitude of deformation bending. And I assume that, I don't know exactly, but I assume that this line may be size of subgrain deformation, subgrain structure, microstructure. And if deformation proceeds further, this deformation bending may lead to grain subdivision, I assume. In view of FEM formulation, FEM modeling, the polycrystal, the grain of polycrystal has different orientations in the FEM modeling state. And if we deform this polycrystal model, the deformation, especially the spin rate of each grain has different value. So there are some discontinuity along this grain boundary region, grain boundary line. This spin rate discontinuity along interface is I think is a problem in FEM modeling. So I assume that the spin rate may change continuously in actual across grain boundary in actual polycrystal. But anyway, we have to solve the problem by assuming the interface of spin rate as a discontinuity in FEM modeling. So we assume that a kind of energy might be lost at interface of discontinuity in terms of virtual working principle or finite element modeling. So let's see the corporate stress or strength formulation again. Even in this formulation, there are no measure to consider the interface discontinuity. If there are some contribution from interface, it should be reflected in corporate stress term. Up to now, we have to do like that. But I assume that the interface, I try to incorporate the interfacial energy into the virtual working principle by assuming the interfacial discontinuity as a continuous change across infinitesimal elements. It is like a limit analysis we learned in high school, as we assume the energy within this boundary layer and limiting the energy term, and we can obtain some residual value. And then finally, I obtained this formulation compared to the previous formulation. You can see this term. This term is the interfacial corporate stress term. Now we have to determine the constitutive model of this term in order to apply this formulation for FEM simulation. Now I assume like this. The interfacial energy is equivalent to grain boundary energy. Actually, I cannot consider other energy than grain boundary energy. So I assume like this. Among grain boundary energy, the simplest one is the low angle tilt grain boundary. If you refer to textbook, you can see the low angle grain boundary is represented by the function of misorientation, a linear function. In the small misorientation range, the grain boundary energy is a linear function, can be approximated as a linear function of misorientation. And considering the fact, I can obtain the interface corporate stress as maybe a constant. By assuming the grain boundary energy is a linear function of misorientation, we can assume the interface corporate stress as a constant. I show that corporate stress has a definitive vector load curve. As corporate stress hardening coefficient increases, the load curve also increases. Like that, the interfacial energy or interface corporate stress hardening is also influenced on load curve. Likewise, load increases monotonically with the value of CGB. The hardness the value of interface corporate stress hardness. It is also a natural consequence, as we added another term in the virtual principle, and so if the hardening coefficient increases, the overall work increases. It is natural. But Actually, we have no definition, exact definition for couple stress and or interface couple stress. However, if we assume that uh, the interface couple stress hardness is constant regardless of material. At least the fact is valid for the low angle tilt boundary report. But if the grain boundary is newly generated, the couple stress within volume maybe decreases. I think it is because the GND or part of GND is accumulated, moved to the new boundary and accumulated there. So the remaining GND density may be decreased. Considering the fact that we can assume that as grain subdivision model, if the grain subdivision increases, the volumetric or couple stress hardening may be decreased. And then we tested some combination of values, and we can see that in some combination of values, the load curve is not monotonically decrease or increase. That means on optimum grain subdivision may be between a lot of candidate grain subdivision. This shows some example. Let's see the surface shape again. As I explained to you, the slip trace is very wavy. Wavy is very curved in case of aluminum, which has high stacking photon energy. But in case of copper or nickel, relatively the slip trace is straight. If you remember the grain-by deformation simulation or using single crystal, you can see that the surface profile or deformation pattern is controlled by the value of couple stress hardening. Then, comparing these two results, we can assume that if slip trace shape is similar to the lattice shape, stacking fault energy effect can be correlated with couple stress hardening coefficient. There are some strong relationship between them. We assume we adopt two assumptions like this. First, we assume that the couple stress hardening, volumetric couple stress hardening coefficient is inversely proportional to the stacking fault energy. And we assume the interface couple stress hardening is constant as before. As I explained, the value of CGB is constant regardless of material. And in addition to this constitutive assumption, we think the following criterion. We think that the overall work is composed of stress work and couple stress work and interfacial couple stress work. The overall work should be minimized. Only we have to do is to define the overall work by adding this term. And then we can, by comparing the simulation result and experimental observation, we can assume that if two conditions applied, the FEM simulation may provide similar behavior with experimental observation. In case of aluminum, stacking fault energy is small. Stacking fault energy is high, and relatively copper. In case of copper and nickel, the stacking fault energy is small, relatively small. And then, if as we assume that the coupled stress hardening is inversely proportional to stacking fault energy, CV value is small for aluminum and large for copper. And then, from the FEM simulation result, we can presume that as CV is small, the deformation shape, mesh shape, is relatively wavy, will be relatively wavy. But in case of a large value of CV, the deformation pattern may be straight. And then, in terms of overall work, as the CV value is small, the work contribution from coupled stress work is relatively smaller than the interfacial coupled stress work. So relatively is compared to copper and nickel. In this case, as the CV is large, the contribution from coupled stress work is large. For both cases, the contribution from interfacial coupled stress is the same, as the coefficient CGB is the same. So, in order to reduce total work, in case of aluminum, further deformation without grain subdivision is preferred to grain subdivision case. If grain subdivision takes place, interfacial coupled stress work is should be included much more. But in case of in this case, as the CV, as the coupled stress work contribution is large, in this case, grain subdivision is better for to reduce total work. And based on this consideration, we can see that the FEM simulation will be similar to the grain agreement, experimental observation. The grain subdivision can be assumed from the number of red line. Actually, this work was previously recently performed, and I tried to find a good criterion if I can. Anyway, I think that grain subdivision is a discontinuous transformation process of material state, and in terms of energy, some microstructural state which can consume less external work would be preferred. I have a question. And based on my simple FEM simulation, I think that there may be some good, some reliable criterion to predict real grain subdivision. This is my conclusion. Today I showed the crystal plus FEM formulation and simulation to predict grain by grain deformation. And I think grain by deformation as well as size effect can be predicted by incorporating strain gradient formulation to crystal plus FEM. And based on experimental observation of grain by deformation, the FEM simulation showed good correlation with the experiment. And in addition, I think for complete crystal plastic FEM, interfacial energy term should be additionally included. And I incorporated the missing energy interfacial discontinuity into crystal plate FEM formulation. And as approximation, I modeled the interfacial energy as the grain boundary energy. And in the near future, I hope to find I have to predict the grain subdivision behavior by using crystal plastic. But for that, we have to determine two model or two criteria. First is constitutive models of interfacial couple stress as well as volumetric couple stress. And second, the criterion to determine the onset of grain subdivision. And thank you very much.
Thank you very much for your presentation. Now we are going to take some questions.